Hello, Physics 1 students. This is our first video describing the concept of a torque. Torque is going to be the way that forces cause things to rotate and twist. So I want to go through and sort of develop it a little bit conceptually, and then we will kind of dive into a more mathematical description maybe in the next video. So the first thing I want you to do is to imagine that there's a door, okay? And your task is to close the door. So how would you push on it? Well, first of all, you have to push, right? It doesn't just close on its own. So you're going to need to exert a force. That's going to be point number one. Need a force. And well, you could think about lots of ways you could apply a force. You could vary the strength of the force, right? You could have large forces or small forces. So I could have a large or a small force or a large force. You could vary the angle at which you apply the force. Oh, going the other way. You could vary the position you apply the force. And when I talk about the position, I'm going to be talking about the distance from the axis of rotation. So this force is applied very close to this pivot point, whereas these other forces are applied farther away. So I want you to think about your experience. We've all opened and shut doors, so we know intuitively what happens. Think about it. Let's rank these here, or not, maybe not rank them, but think about how much twist action this little force up here is going to cause. Not very much. In fact, even if I make it larger in magnitude, make it a big force, you still don't get very much twisting because it's just right down the door frame, or the door itself. So let's see here. So somehow the angle is important. And in fact, of these three forces up here, I would kind of expect the one that's more perpendicular to give more twist. So it's better at 90 degrees. And then the other observation is that you get more twist when you have more leverage, when your force is displaced away from the axis of rotation more, not applied right at the point. It's kind of like using a hammer even, and if you use a hammer and you grip it right near the head of the hammer, you don't get much power. But if you hold it near the end of the handle, then you can swing it much faster. So grows with distance. Okay, so these are the three observations. The amount of twist you get grows with the force, it's better at 90 degrees, and it grows with distance. So roughly then, if I wanted to define something which depends upon these and will measure how much twist a force will exert, then I would want to define a combination which would be, well, okay, so I need it to grow with the force. So I'll just, for right now, I'll call it twist. So the amount of twist you get is going to go something like the size of the force. It's going to grow with a distance or lever arm. So I'll call it R here. So this is the lever arm. And then it's supposed to be maximized at 90 degrees and 0 when the force is applied right along the lever arm. So I need a function of angles which is biggest at 90 and 0 at 0. My options are, I guess, sine or tangent, but tangent of 90 is is ill-defined, and I want this to always be defined. So I'm going to define it to be sine of an angle. I'll define this more precisely in a bit. We've seen this kind of combination. This is a cross product. Okay, so a torque is going to be related to a cross product between a force and a lever arm, or sometimes we'll call it a moment arm. So I'll go ahead and define it. So I will go ahead and kind of draw a general situation here. Let's imagine we have some axis of rotation. Usually I put an X there, some axis of rotation. And then, so maybe we have some shape, okay, whatever, it could be a pulley or something. And then we can imagine there is a force acting on it. So what I want to identify more carefully is the lever arm extending from the axis of rotation out to where the force is applied. And then the vector from that point here would be my force vector. And the angle I want to talk about is the angle between the lever arm and the force vector, and it should be less than 180 degrees. So I'll call that theta, where theta is always chosen to be less than 180. I guess it could be less than or equal. Okay, it could be equal to 180, but it can't be greater than 180. So you always choose the smaller angle to do this. Okay, the definition of torque is going to be the following. Torque is defined to be, well, first of all, the symbol we will use is a Greek letter tau. It's not a T, it's a Greek letter tau. It will be a vector quantity, but it, like all rotational quantities in this class, it'll point in the Z direction for a rotation in the XY plane. And the magnitude of the torque is going to be the magnitude of the lever arm, or moment arm, it's sometimes called, the magnitude of the force times the sine of the angle between them, where the angle is less than 180. R is the moment arm or lever arm, and is just words for the same thing, and it points from the rotation axis to where the force is applied. The force is the force. There's no mystery there. And that's what you get. So just some observations here. We have these two vectors. So we have R, and we have some force F. And then we have this formula, RF sine theta, for when I write it out in terms of magnitudes. There are a couple ways you can think of this. In fact, let me redraw this just to make, so we don't get worried with angles bigger or less than, we're going to work with angles less than 90 degrees, but the formula I write down works more generally. So I'm going to redraw this so that I have R, and we'll have a force here oh, let's choose the force to be like this. Okay. Here's my axis of rotation back here. And the angle between them is right here. Excuse me. So how can we interpret this? Well, basically what you can do is you can either think of this as R times the quantity F sine theta, or you could regroup it and think of it as F times R sine theta. What does that accomplish for you? Well, if I think of it in the first way, look at the force vector F. F times sine of theta picks out from the entire force, it picks out the perpendicular component. When I say perpendicular, I mean the force, the part of the force which is perpendicular to R. So in fact, I can think of this as F as R times F perpendicular. That's one way to think of this. The other way, redrawing for the same R and the same force, and I have a angle theta here. The other thing you could think about is if you group sine theta with R, you could actually think about this as giving you the part of R which is perpendicular to F. So then you could think about this as the whole force times just the perpendicular part of R, or you can think of it as the full R times the perpendicular part of the force. It does not matter. You're just shuffling things around. And for different problems, it may or may not be more useful to use one or the other. But it's always the perpendicular information that contributes to the torque. So I reiterate, you can either think of it as the full lever arm times the perpendicular part of the force, or you can think of it as the full force times just the perpendicular part of the lever arm. So that's kind of a nice picture of what's happening. All right. Let's rewrite this using cross products now and go the full treatment. Okay, let's go through the full treatment. So given a vector field, or just a vector, I don't know, let's call it V, and an axis of rotation, we can define the moment of the vector field, V, lots of words, is defined to be, I don't really have a good symbol in general for this, so I'm just going to leave it like that. It is defined to be the vector from the axis to where the vector field, to the point where the vector field is defined, cross V. So this would be the moment of V. And you could do this with any vector field. However, so for example, it turns out that V tangent to a circle is R cross omega, where omega points in the z direction. We saw this when I talked about angular quantities as vector quantities. So I could say, if I wanted to, that the tangential velocity is the moment of angular velocity about the axis. So you could use the same language. No one does. Well, I'm not aware of people doing that, but you could. Where people do use this vocabulary of a moment is when talking about forces. So we can compute the moment of a force about an axis. So here's let's pick an axis of rotation. And let's imagine I have a moment arm, and then imagine I have a force acting some direction, and this is going to, right? So I've got some, sorry, we draw our lever arm. It should always be perpendicular here to the axis of rotation. You know what? Let's just draw this like a top-down view, so it's clear. There we go. And then we'll have our axis of rotation here. So we talk about the moment of a force about an axis, that would be, and that one does have a symbol. People write that with an M as the symbol. The moment of the force about the axis equals R cross the force vector, cross F. So in general, the moment of the force is just the definition of the moment of a force. Because this one is a special combination force, we will give it a name. This is the moment of a force, is also called the torque due to the force. Right? So the torque due to a force is the moment that the force produces. Now, those are mathematically correct. Linguistically, it's a little bit, this isn't quite how people use it. Linguistically, especially in engineering, when you have an object, let's say we had an object which has let's say it's a turntable on, spinning, being spun by some sort of an axle, and then there are external forces acting on it. Right? So what we would have is that there are torques being generated by the axle, and then there are also torques being generated by this other force. And language-wise, I believe in engineering, people tend to say torques at the axle. They say torque. The torque is that which is caused by kind of like an internal axle. I think I can say that fairly. Internal axle. It needs to be an E there. Axle, or I don't know, internal. Yeah, just sort of the internal pieces. Whereas they will talk about moments of force, and those are caused by external forces. So, excuse me, I apologize. And furthermore, this is also often shortened to be just the moment. So they don't say moment of force, they just say the moment. And what they mean is the torque caused by external forces. When they say torque will refer to moments caused by internal forces or internal structures. That being said, in physics, I just tend to call them all torques. So, and I would probably do that without even noticing. But mathematically, they're all the same thing. All right, so I've defined, given some axis of rotation, some pivot point, I've defined a moment or a torque due to a force as the moment arm or lever arm cross the force. And it measures the amount of twist we get from a force. We kind of know that from everyday life. And you can think of it as at least the magnitude of the torque, you can think of it as the lever arm times the perpendicular force, or think of it as the force times the perpendicular arm. Either one is the same because both are just an interpretation of the trigonometry encoded in the cross product. One other comment, most of the time in this class, we will have rotations in a plane. So for us, couple comments. Usually we will just talk about the torque as being positive or negative, where positive torques are going to want to cause counterclockwise rotations, whereas negative torques want to cause clockwise rotations. In a 3D context, the torque vector, or the torque should be a vector. And then kind of combining that with the 2D problems, we would see that a torque describing, so a torque vector describing a 2D rotation will point, this is 2D rotation, will point in the third direction. Which we will take to be the z hat direction. This is just like what we had for omega vector and alpha vector. So if you don't remember that, you can go back and look at the videos where we describe how to give these rotational quantities a vector interpretation, and the vector that you get for a rotation in the plane is that it actually points in the third direction, in the z direction. Okay, so I'm going to stop there. That's sort of the definition of vectors, and then, of torque and moment. In the next video, I'm going to describe how we can use torques to study the motion of objects.